Now it's doing my microphone. Okay, so if you wanted to relive the magic later on, you can always watch the video. For now, though, we are moving on to, wait, why is this? Yeah, this is what I want. So moving on to something, hopefully it's relatively interesting and fun. We'll see. And we need to talk a little bit about homework. I did a revamping of the homework online, so you'll notice all kinds of weird web links. I'll show you those before we leave. So first off, though, Euler's theorem says that this is in regards to a graph. So if a graph is connected and has no odd degree vertices, then it has an Euler circuit. This is just a rehash, sort of a review of what we did. You remember all those beautiful graphs and trying to draw them without picking up your pen from the paper. So anyway, if a graph is connected, has no odd vertices, then it has an Euler circuit. If a graph is connected and has exactly two odd vertices, then it has an Euler trail. I think that's the word that our book uses. I'm going to change that to trail. Doesn't matter. You don't really need to write these down because you already know this. I'm just reviewing this. So we did this already, this idea that, that if you have two odd vertices, you can have an Euler trail. You start at one, end at the other. And if this graph has more than two odd vertices, there's no way to make a trail, no way to make an Euler anything. So we went over this question. Once again, this is just review. What's wrong with being odd? And what's wrong with it is that you can approach. So if we have an odd vertex here, we go towards it, we go away from it, and then eventually go towards it maybe again. But whatever the situation is, there's an odd number of edges. So even if it's 5, we go away, and then we come back. We'll either get stuck there or we have to stop there, or start there. Start or stop at an odd vertex. So that's sort of a sketchy proof of this theorem, but we kind of went over this before. What I want to explore today is the idea that even if you don't have a graph that has an Euler circuit or an Euler path, we can fix it. We can fix this graph. Now, we have to make some adjustments to the graph, but we can fix the graph. So let's take a look at this graph to start with. This is one of the ones on your little page there. So what I'd like you to do is just tell me, does this have an Euler circuit or an Euler trail, or is it just nothing, neither? So go ahead and count up the vertices, the degrees. We'll go ahead and see if we can answer this one. I can pick volunteers. This one's fun. Let's see. There you go. Joshua, does this have an Euler circuit or an Euler trail or any Eulerism things? Well, why do you say that such a thing? He thinks it does have an Euler circuit.
Because there's no odd vertices.
That's exactly right. Euler's theorem says that if you have no odd vertices, that's number one there, there's an Euler circuit. And so we could find it. I'm not going to bother, but let's go around and make sure. So you could go around yourselves and find, whoops, that's a 4. This is a 4, 4, 4, 2. All of these numbers are even. And so we can start. These are the degrees of the vertices. They're all even, so we could start and end anywhere, and you can make your Euler circuit. I forget what I put on that page. Let me just see. I'll pull it up here. I think, is this one on? Hey, welcome. I think this one, is this one on there? That's the next one? No, that one's not on there. Oh, good, because that one's kind of boring. Well, you can look at it. We won't bother. Yeah, the next one is going to be interesting. But this one's kind of boring. So you might wonder, why do I say it's boring? Well, go ahead and tell me if this has an Euler circuit or an Euler trail. And meanwhile, I will pull up, that way I'll know what you're looking at here. There we go, my graphs. Ah, yes, yeah, that one, the next one is more interesting. So let's find another volunteer. Lucas, what do you think about this one? Does this have an Euler circuit, Euler trail?
I think it has an Euler circuit.
And why would you say such a thing?
All of the vertices are either degree 2 or 6.
Oh, very nice. So they're all nice. That's a great way of putting it. They're all either degree 2, lots of degree 2, but then you have these 2 in the middle here that are degree 6. And so, yeah, all of them are even. So we go back to Euler's theorem and say, hey, this one has an Euler circuit. Start anywhere you like, end anywhere. Well, you're going to end where you started, of course. Of course, this is the problem with this graph, the bridges of Königsberg. You had a degree 3 vertex, degree 3, degree 5, degree 3. Too many odd vertices, no Euler circuit, no Euler trail. However, if you were with your special friend in Königsberg, you still might want to walk all 7 bridges, and you might compromise and say, okay, I know that I can't walk them all once and only once without retracing my steps. And so maybe we can make a compromise and say, let's cross as few bridges as we can. In other words, can we do this in such a way, what's the minimum number of repeat bridges that we would have to do in order to walk the bridges of Königsberg? So that's the sort of thing that we're going to do next. And this is a technique that's called Eulerizing or Eulerization. And so what this does for us is it allows us to take a graph that doesn't have an Euler circuit and make it have an Euler circuit. You might wonder why. Why would we care? Well, the reason why we care is because we care about this guy. This guy is dutifully getting rid of all the snow on the paths here at MVNU. Where does this person have to drive? He has to drive his little buggy on all of these paths here. Now, take a look at this graph. This is way too complicated for us to actually do, but if you were tasked with driving that little buggy along all of these paths and clearing the snow, you might notice that there are a lot of degree 3, 1, 2, 3, 4, 5, degree 5, degree 3. So many odd vertices on this campus, there's no way you could do it without retracing your steps. At least there's no Euler circuit. But what we could do for this guy is we could come up with an Eulerization of this. And the goal of the Eulerization is to come up with a graph that could be superimposed on this, and it shows you which of the edges you have to duplicate in order to do your job and clear all the snow. Anyway, getting back to this. So I've got this graph for you. So let's go ahead and answer some questions about this. You've got this on that little piece of paper I gave you. So question number 1, which of the vertices are odd vertices? Because the odd ones are the problem ones. So take a minute, figure out which ones they are. And I honestly don't really care what the degree of those vertices are. I just care which ones are the bad ones. I want to know the bad ones. Gina, which ones are bad?
A, B, C, D, E, F, G, H.
A,
Basically all the ones on the outside.
C.
D.
Oh, D is okay. It's got
Never
2.
mind. Yep, D and H are fine.
E, F, G. That's okay. One of the properties we talked about last time or last week was that there will always be an even number of odd vertices. This is important for Eulerizing because if there are an even number of odd vertices, then you could pair them up. You could say, okay, you two. Let me show you what I mean by this. So this one I could pair with that one and say those two are bad, but we're going to lump them together into a category. You'll see why I'm going to lump these together in just a minute. Some of you can probably guess. And then these two, those are bad, but we can put them, they're friends. They're near one another. And then one more pair, just to show you this, that pair, E and C. They're near one another, so we'll lump them together. Now here's the deal. Let's say that this was the diagram or the graph, the map of some college campus, and these are all of the paths that some person in early morning hours has to go and get rid of all the snow on these paths. Then these are the places that prevent that person from making an Euler circuit. But what we could do is we could say, okay, F and G, they're both bad. Well, how about this? What if when you get to F and G, you just repeat that particular stretch? I know the snow's already gone. You did a good job. You got rid of the snow on this path. But when you get to G, just go back to F and just repeat that one edge. Notice what I've just done there is I've added an additional edge to this graph. And now what's happened to F and what's happened to G? Are they still bad? They're not bad. Both of them have 4. So we're good. So let's get rid of those bad circles. No longer bad. Now F and G are good. I should probably leave the circles. In fact, I'm just going to clear everything. Sorry. Here's how I Eulerize a graph, just so you know, is I identify the odd vertices, I pair them up, and then I connect them. So those two are going to be connected. And all that means, all that signifies is that when the snowblower gets to this edge, just do it twice, even though you don't need to. So let's see, what are the other ones that we paired up? Here, this one to that one, those got paired. So when the snowblower gets down here to edge AB, just do it twice. You'll be fine. And then C and E, oh, we've got a problem, don't we? Now, don't write this down. So what I'm about to do, don't do this. It's tempting to just draw that. Now, that's fixed things, hasn't it? Now we have, this has an Euler circuit. However, notice what this would represent. If this graph were representing some college campus and the paths that this particular snowblower has to cross or clear, then from C to E, what that would represent would be something like this on our college campus. Let me find a couple of odd vertices here. Now I can't, oh, here's one. So there's an odd vertex there. 1, 2, 3, 4, 5, 6, darn. Okay, this one is an odd vertex here. Okay, we'll pretend that that's an odd. I know it's not really. So what that would represent if we just connected these is when you get over here, snowblower person, just cut through the middle of the quad and then end right there. And I don't think that would make certain individuals on this campus very happy to see these, tire tracks right through the middle of the beautifully, beautiful snow, because it looks nice when it's in the middle of the quad, but we don't want it on the path. So we don't want to make, where's my thing there? There it is. Nope, there it is. So we don't want to make any new edges. We just want to duplicate old edges. So if you can imagine what's going to happen when this snowblower gets to point C, we could say, okay, instead of repeating, there is no edge between C and E. Instead of repeating that, since it doesn't exist, let's go up here to D and then over to C. You could also go over to I. But notice what I've done there is I've added 2 edges. However, everything is good because these 2 vertices, they were formerly odd vertices. Now they're even, which is my goal with Eulerization. And the other vertex that is involved in this situation, D, it was even to begin with. I added 2 edges. It's even afterwards. So anyway, that's just an Eulerization. Why is this not advancing? I don't know. It's not advancing. Okay, well, I guess we don't care. Why does it not advance for me? Okay, well, apparently there are words there that you don't care about. I can't even read them because it's so small on my iPad. Okay. Basically, the words say add edges to make this an Eulerized graph. So we add an edge here, 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 and here. Notice that what you're left with is now a graph that has all even vertices, and the duplicate edges just represent duplicating whatever you're doing, whatever problem you're solving. And then you want to add the minimum number of edges so that every vertex has an even degree. So let's go ahead and take a look at this one. This is your next one, and I want you to Eulerize this. Step 1, you're going to identify all of the odd vertices. Step 2, try to add the minimum number of duplicated edges. So this might be a street network that some police officer has to walk around the street network and cover all of the streets, or better yet, a postal worker delivering mail. This sort of thing that I did between college and grad school. I delivered mail for 6 months. Had to walk street networks like this. So I suppose that I might not have, picked a good graph here. Does this have an Euler circuit to begin with? Joseph, what do you think of this graph? Does this thing have an Euler circuit? Does it have any odd vertices? Quite a few odd vertices, and so we go back to Euler's theorem, and it says if a graph has more than 2 odd vertices, then it cannot have an Euler trail or an Euler circuit for that matter. So too many odd vertices, you're right, no Euler circuit. All right, Sarah, where are all these odd vertices that Joseph is complaining about?
All edges except the corners.
Okay, everything on the outside, all of these, boom, boom, boom. All right. All right, so we're going to have to duplicate some of these edges. Imagine if you're walking around this particular street network, you would have to duplicate some of the edges. Pearson, where am I going to put duplicate edges?
So for some of them, it'll go like to the corner and the other one, but you can do. If we start between A and C, you can connect those two. Then you can. Sorry. I think you have to connect. No, there's 2 different ones. I did the same thing for you. Different corner of the paper.
Different corner? Okay, so we could just keep going. Let me do this. Let me just connect these up. It just depends on what we're going to pair. So I'll follow Pearson's lead here and just connect up and down. There, I did it, didn't I? I think that the new graph, if you include the red edges, my new graph has all even vertices. There's a bunch of vertices in the middle. They all have 6 edges. And all the ones on the outside have either 4 or the corners have 2. So I did it. This is not right? Well, I mean, this does have an Euler circuit. Now, by not right, do you mean that you just don't like it? No, it can be better. So you want to do a better job than me? Okay, let's get rid of this and do a better job. You're right. I just was fooling around here and wanted to show you that you could do it, but you might not have the best. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so currently the record is 11 duplicates. Let's see, just a minute. 11 dupes. So we got 11 edges that are duplicated. Let me get rid of this, and then someone who wants to try to beat my 11, you can go ahead and tell me what to do. There they are. Okay, who can beat 11? You got it?
I think so.
What do you got?
You can do the same things on the ends, where you do like the twos.
Like this.
Yeah, like that. And then for the top row, you do the first one connected to the second one. And then the bottom row, you do the first one connected to the second one. And then you do the middle.
All right, 1, 2, 3, 4, 5, 6, 7. Ooh, 7 dupes. So far, new record. Can we get it below 7?
So why can't you just connect
Oh, just a minute, just a minute. Let me erase. So Gina's method gets rid of the 7. Okay, what would you want to do?
Why can't you just get rid of sorry. Why couldn't you connect the middle one to 2 pairs?
Oh, interesting, on top. So you're saying do this, and that fixes, and then keep going. All right, so yeah, let's examine that.
This one's fine.
Do they
then you'd only have 2 odd vertices.
Okay, now we only have 2 odd vertices. We still, oh, interesting. So now we could make an Euler trail. Yeah. So if the goal, now we just have 2 odd vertices. So we could just make an Euler trail now. The problem with that is that if you imagine this situation, this guy, he's got his little thing parked down here, let's say, and he's got to put it back in the garage at the end of his shift. So so it'd be nice if we could make an Euler circuit. So we could connect those up now that we've only got 2. Let's just do this through the middle. But I think that's going to give us too many. 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, that's 9 dupes, which is better than my solution. But I think 7 might be the best you can do. Can you do better than 7?
Definitely not, but I have a question.
Yeah.
If we have this situation, and you get rid of the 3 lines in the middle, would you be able to just add another edge to one you've already repeated? Would that fix the issue? At least with the vertices? I don't think it would be a circuit by any means, but
Wait, what do you mean?
yeah. So on either one of those
Like,
edges on the top.
do that?
Oh yeah.
Okay, that fixes the middle one, but it's like a rug that's a little bit too small for your room. Now this one is bad. Yeah. So you always have to go back and double check. All right, let's try again. Let's see. Do you have this one? This one's boring. You have that one? I hate that one. Let's move on to this one. This one's more interesting. So see if you can Eulerize this and do it as efficiently as possible. And to help you out, I have labeled the bad vertices. So you can see there's 4 odd vertices, just 4 this time. So amazing. Let's just create. The one below, sorry, yeah, it's the one down, the odd one, the odd ones.
Oh, that's right.
Okay, good job. All right, let's see what we're going to do here. So I'm assuming that, so if you tell me, for example, that you want me to connect X and Z, let's say, I'm assuming that you probably don't want me to do this sort of thing, going around the outside and adding way too many edges. So when you say add, so basically I'm just going to ask you which of these pairs, basically pair them up and connect them up. So that would be kind of silly. So let's see how we did here. Sam, how did you do this? Which of these pairs did you pair up? Okay, so you probably did something like this. Maybe you went around the outside, but you added 3 edges to go from X to W. And then Y and Z, either one way or the other, you're going to have to go around the outside. And so that's a total of 7 edges that we had to add. And that would fix things. So what else? Does anyone have a better?
I have a question.
Yeah.
So you can't connect X, W, and Y together, right, by a central node?
Okay, let's try. I think that we've dealt with this, but we'll deal with it again. So you mean something like this?
Yes, and then connect Z to Y.
Okay, well, let's just deal with this first.
Okay.
So look at that, that so-called central node. So we're not connecting these up like we're connecting electrical circuits or trying to plug things into the wall. The goal is to pair them up and connect them to one another. In this case, that central node has 7 now. And so now you've taken the problem and you've moved it. Y is no longer the problem. Now that central thing is the problem. So yeah, we don't want to do that. So whatever you do, so you go ahead and find your solution, double check that you haven't messed anything up, because you're like, oh, let's just show you this. Let's fix Z. There, Z is fixed. But then you're like, wait a minute, I just messed this up. That's now 3 instead of 4. So it's not good enough to just fix the bad ones. You have to make sure you don't mess up anything that used to be good, turn good into bad. All right, but we had 7. Anybody get better than 7? I'm guessing that some of you had 7, but you did it a different way. Like there's other ways to get 7. Like this, we can connect those up and then connect these up. That's 7 as well. And each of those just represents duplicating. Oh, wow, it's going to be little, isn't it? And I got to log in. Give me a break. Just a minute. It's so little. I'll do this on the computer. Just a sec. I'll pull this up here. Oh, it's so low. Like on the floor. Okay, so yeah, I was just going to show. Okay, while we're waiting for that, so the road trip thing. The question I have for you is, can you cross? Now, this is kind of a stupid thing that you would do if you were taking a road trip. You wouldn't care so much about crossing each border once and only once, but that's the question I have for you. Now, this is going to lead into the more interesting question for this particular graph, but what I would like to do is to come up with a graph that represents this situation. So here's the situation. We have different states. This is just the southeastern United States. So each of these states could be represented by a dot. I don't care where the dot goes. You could try to stick it at the, what is it called? The capital of the state. I don't even know where the capitals are for these states. I'm just going to pretend. And then I want to have an edge representing each border. So this is going to be a little bit weird, but the border between West Virginia and Virginia, no matter where you cross it, whether you use Route 64 or Route 77, it doesn't matter. You're going from West Virginia to Virginia. And so I'm going to put an edge between those. Same thing with Virginia to North Carolina. There's lots of ways to go. You go right, Route 95, Route 77. There's probably others. Little tiny roads you could take, Route 52, US 52. But anyway, lots of different ways to get. What I'd like you to do is to make your graph, and then I'm going to reproduce it over here. So notice I've got the same thing. This is going to be West Virginia. This will be Virginia. Down here, North Carolina. And so I'll just go ahead and put my dots in. Let's see, Mississippi. I almost forgot Florida. There we go. Okay, so tell me where the lines go while I get this thing that I wanted to show you. All right, this is just sort of a silly thing. I was dealing with my mother's house It's back when she had her stroke and I had to sell it. But anyway, I was going down to Charlotte a lot. And one of the times, I brought my bike every time. I decided I would ride every single road in her neighborhood. And so there it is. I guess you might say, you missed Boyce Road. Well, I did my best. You can see. So I had to repeat lots of roads when I did this. Lots of cul-de-sacs in that neighborhood. But that was an Eulerization of that particular neighborhood. If you don't include this, which I probably should have. Kind of disappointed with my former self. Well, anyway, so that's the only thing that I thought was kind of funny about that. Let's get back to this and see if we can get these connections so that we can answer the question that we're going to do here in just a minute. Okay, so what do we got here? We've got West Virginia to Kentucky, Kentucky to Tennessee. Tennessee is connected to a whole bunch. Oh, wait, Kentucky and Virginia are connected, aren't they? See, there's that border there. So each line just represents the fact that these two states touch one another. And you can go from one state to the other directly. That's what the lines represent. So Tennessee and North Carolina. Wow, Tennessee and Georgia, Alabama, Mississippi. Okay, and then these are all connected here, here, and here. Florida and Georgia, Florida and Alabama. I feel like I'm missing some. Oh, Georgia and North Carolina share a little tiny piece of a border right there. So if you don't like South Carolina, you can always go from North Carolina to Georgia by going around the corner, sort of. I think I got them all. Let me know if you're seeing anything I've missed on my graph. Oh, yeah, Virginia, Tennessee. That's a similar situation. Virginia connects with Tennessee. And if you don't like North Carolina, you can sneak from Virginia to Tennessee and avoid. Maybe there's like a open warrant out for your arrest in North Carolina, so you're trying to avoid that state. So there it is. Anything else that I've missed? I think I've got them all now. So the question is, can I cross each border once and only once? I guess let's start with that. Does this have an Euler trail? It does? Wait, how? And Kentucky and Georgia are the only odd ones? Interesting. So I suppose what I could do, if I wanted to do this silly road trip, is I could fly to Atlanta, rent a car, and then drive across each border once and only once, end in Kentucky, and go to maybe Lexington, drop off my rental car, and then fly out. That would do it. Yeah.
So it says that you can cross each border once and once. Why would you not just go in like a large U? Like West Virginia, Virginia, North Carolina, South Carolina, Georgia, Florida.
Okay, 2 seconds. So starting here,
Yeah.
go down, and then back up. But then we missed these borders.
So maybe I'm just not understanding the question.
Yeah, the question is ridiculous. Why would anyone want to do this?
You're crossing like
each actual physical land border once and only once. Yeah, so I go from Virginia to North Carolina, and that's the only time I cross that border. But then later on, I want to go from North Carolina to Tennessee and from North Carolina to Georgia. I don't know why you would ever want to do this. Maybe so you can stand on the board. I don't know. This is stupid. This is dumb. You're right. Why would I ever want to do this? It seems much more obvious that a road trip, like if you had your spring break, you wanted to plan your spring break, it would make more sense to try to visit each state. That's what matters, because even if you cross into Virginia only once, you could get your photo next to the Welcome to Virginia sign. And then same thing with North Carolina. So you just need to visit each state once, and then you would do just the big view. And that would make so much more sense. In fact, that is part 2 of this road trip problem. You visit each state once and only once, and that makes so much more sense. Because why would you that's just dumb, cross each border once and only once. So this one makes more sense. And so this leads us to this new type of way of looking at a graph, and this is called a Hamiltonian circuit. Hamiltonian circuits, you visit each vertex once and only once, not each edge. So notice Euler, this is easy to remember. Euler, you visit edges. Hamiltonian, you visit, oh, doesn't quite work, doesn't it? What if I do it this way? Okay, now that V kind of looks like an H, or an H that looks like a V. Yeah. Anyway, so Euler is edges, the other one is vertices. So I'll just go with vertices here, vertices. So the reason why you might care about this, Euler circuits, you would care if you're delivering mail, clearing snow off of roads, walking a beat if you're a police officer, those sorts of things. Hamiltonian circuits, there are various things that you might be interested in, but the Amazon driver driving to various houses, you just care about getting to all the houses. You don't care about driving all the roads. Same with the UPS driver. Those sorts of things. Another interesting thing is if we were producing a circuit board and you wanted to drill holes in that circuit board in certain locations, then you would just want to guide the drill, boom, 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 and you're done. And then you go back to the beginning so you can drill holes in the next circuit board or whatever it is that you're doing. So CNC machines might be interested in Hamiltonian circuits for that reason. So Hamiltonian circuits, I need to know what is next on your little piece of paper there. Hold on a sec. So we just did the graph, the map. Oh, are we on page 2? Back. Oh, yeah. Okay. So save that for a minute. Save that for a minute later. Okay. So what I'd like to know is, can we do the same thing we did with Euler circuits? Euler circuits had this nice rule, Euler's theorem. And so I want to know, can we do the same thing? I'm going to make this easy for you, though, and say that the answer is no, you cannot do the same thing. So I know that says Eulerize. We're not going to Eulerize this time. I'm going to explore this in terms of Hamiltonian circuits. I want to visit each of those dots once and only once. And I want to know, how do I do it? You got a way?
You need neither make it just going basically
Left
left to right all the way down.
to right, all the way down?
Like A, B, then go down a row, then just go back across.
All the way?
Yep. And just repeat that.
Okay, it's supposed to be a circuit, though. And I didn't make it back home.
Easy then. You can just take the middle row and like bump it over to the right one.
Okay, just a sec. Let me see if I can bump it over. Over here, down, over, down, like that? Yep. Okay, very good. Okay. So this does have a Hamiltonian circuit. Pardon me. So if the UPS driver or the Amazon driver had to deliver to all of those houses, pardon me, the most efficient way, or at least one efficient way you can do it, is just start there, deliver, and then you get back home, or back to the warehouse or wherever it is. Very nice. Okay, what about this one? I want to know, is there a Hamiltonian circuit? Hamiltonian question mark. Can't we do the same trick we just did? Oh, this one doesn't work out as well. Well, let me give it a go. So we'll try the trick that we just did. So we start, we go over, we come back. Don't go all the way back, though. Go over, and then, oh, wait a minute. We get stuck. But that doesn't mean that we can't do a Hamiltonian circuit. Maybe we can. Let's see if we can fix things up here. Maybe if I'm more clever, that's the problem. If I start here, and I go down and up, and then maybe over, down. Look at this. This is, I like this. I did it. Got them all, didn't I? I missed one? Oh, yeah, I did. I was doing good, but yeah, there's that one. So in this case, we won't prove this, but it's not terrible to prove this. This one doesn't have a Hamiltonian circuit. This one does. This one doesn't. So how do we know? Well, that's the problem, is there is no theorem like there is with Euler's theorem. So you can't just look at a graph and know that it has a Hamiltonian circuit. There are certain classes of graphs. For example, these graphs, these grids, you can tell whether they have Hamiltonian circuits. I'll just cut, well, yeah, I want to make sure we get to the back page here because it's fun. Man, well, this is fun too. Okay, so when does a grid have a Hamiltonian circuit? So that's the question that we'd like to answer. Man, yesterday I thought I'd get through all of this stuff over here. What in the world? There's like 47 slides, and we're on slide 26. I got too excited. Okay, so that's terrible handwriting there. Let me clear it. So here's the sort of question that we'd like to ask is, when does this graph have a Hamiltonian circuit? Here, this 3x4 grid, if you want to think of it as 3x4, this does have a Hamiltonian circuit. This is the one that we did just a minute ago. The other one that we did, the 4x4 grid, does not have a Hamiltonian circuit. So can you tell just by looking at the grid, if you have a grid graph like this, when it has a Hamiltonian circuit and when it doesn't? What about a graph like this, a polar graph? Can you tell when this sort of a graph has a Hamiltonian circuit? I'd kind of like to know. So those are sorts of questions that are fun to answer that maybe we will save, or maybe I'll just assign them to homework. That would be even better. So here's two graphs, though. So to get a hint as to why certain graphs have Hamiltonian circuits and certain graphs don't, here are a couple of graphs that do not have Hamiltonian circuits, and maybe you can explain to me why they don't have Hamiltonian circuits. But take a minute, see if you can figure that out while I look at the homework and weep. No, I'm not going to weep. It's just I'm sad that I I was too ambitious. Look at this. I'll make adjustments. All right, I'll pick someone in just a sec. So you can think about those. Why did you not have a Hamiltonian circuit? What is this? What is this? Oh, there was homework listed for today. I don't know if anyone saw it. There was. When I went to change the homework last night, I realized, oh, there's something listed for today. I didn't know if anyone did it. Okay, no one. Okay, that's totally fine. I didn't want to delete it in case anyone did it, but since no one did it, I will delete it. 537, 1, 5, and 8, some random graph type problems. Darnio. Just a minute. Okay, so while we're waiting for me to get myself straightened out, it may have to wait until after class. John, pick one of these two, the one on the left or right. They both don't have Hamiltonian circuits, but can you explain why? Pick one.
I feel like I can do the right one easier.
Okay, tell me about the right one.
It's got this, I mean, if you divided the graph in half, and there's only one connector between the two, so once you do one side of the graph, you have to go to the other side, but then in order to get back to the other side,
no way to get back. Yeah, so you'd have to repeat some vertices. So yeah, so that's a good way of putting it, is that you have this graph that you could separate into two chunks. There's like this bridge between the two. So it's like you have two islands with one bridge. So you could visit all of these cities or vertices over here on that island, and then you go over here, visit all those, but then you're like, how do I get back? Well, I'm gonna have to go back through those two cities to get back home. So that's a good way of putting it, is anytime you have two subgraphs that are connected by a single edge. There's no Hamiltonian circuit. All right, what about this other one? So Peyton, do you have any ideas on that first one? Like,
Same thing what he said.
same thing, but this one can't be broken into two groups. It is similar though. So what are the two groups that you're thinking of? So here, just to show you what John was saying, is you have these two groups, and they're only connected by one edge. There's not two groups like that, but there is a similar sort of situation over here. Here, let me give you a hint. Let's start here. Try to come up with a Hamiltonian circuit, starting with that.
Well, you either like can't get to the, you can't connect the B to the C.
Yeah, well, I could do this. I could go to B first, and then go to C. That would be
Sorry,
okay.
but you can't get to the other side.
So there's always going to be someone left out. Yeah, I guess now the only place I can go is back home. So that didn't work. So we could start at A and we go to C first, and then we'll go to D. Oh, now we left out B. So yeah, it has to do, it's sort of similar to John's situation, whoops, except for in this case, the situation is that you have these three sort of paths from A to C, and you're going to have to use one of them to get from A to E, from A to E, and use another one to get back, but that's going to leave one of them out. So yeah, someone gets left out.
This really, so both of these have a Euler trail.
Euler, yes.
Oh, sorry, yeah, Euler trail on an Euler circuit. Does that have anything to do with it?
No. Because like here, this graph doesn't even have an Euler trail, and yet it has a Hamiltonian circuit. So yeah, no, it's not related. Sadly, because yeah, it would be nice. It'd be nice if there was a relationship, because then you could say, oh, here we can make these connections. But there is no rule. So that's the irritating there. There's no general rule for Euler or Hamiltonian circuits, but there is a rule for certain types of graphs. So I think if I can find it, I think this is on your homework, and I think this is on your homework. Basically, if it isn't, I will actually write it into your homework. I'll have to chop your homework in half or something. But basically, your job will be, tell me if you have in by M, a grid. Can you tell just by those two numbers whether or not you have an Hamiltonian circuit? And the same thing back here. I think this is called a wheel graph maybe. But here your in is the number of rings, maybe R for rings, and S for spokes. So if you know those two numbers, can you tell me, is there a Hamiltonian circuit or not? So I might actually have to write this up to put it online. But there is one class of graphs that for sure has a Hamiltonian circuit, and that is a complete graph, a graph in which every vertex is connected to every other vertex. Here's some examples that are really hard to see. Oh, why does this do this? Okay, there it is. So this is a graph with two vertices, and it's complete because every vertex is connected to every other vertex. Now that doesn't, it does have a Hamiltonian circuit because we don't care about repeated edges. So here's the circuit. Start here, go there, go home. That's it. So that's a Hamiltonian circuit. Most of the Hamiltonian circuits, though, will not repeat edges. In fact, this one, complete graph with three vertices. 1, 2, 3. Here's the Hamiltonian. Check it out. I did it. I know, it's amazing, isn't it? Okay, here's four vertices. So you have to understand that there is no connection here in the middle. We're just interested in those numbered vertices, and each edge is connected to each vertex is connected to each other vertex. And there are various ways there are a couple of, maybe 3 different Hamiltonian circuits that I could draw on this. I'll just draw one of them, or no, I'll just point it out to you. Starting at this vertex, we'll go up there, then we go down through the middle, over, and back. That's a way to do it. So I definitely wouldn't draw this on your paper because you might get in trouble with someone else. And the pentagram there, But anyway, I guess with a circle around it. Isn't that the pentagram symbol? But anyway, this one is a complete graph with 5 vertices. Here's 6, 7, 8, 9, 10, 11, 12, and so on. What's interesting about these is because there are so many edges, you're guaranteed to always have a Hamiltonian circuit. In fact, there are not only, there's many Hamiltonian circuits. In fact, what is it going to be? N minus 1 factorial? Hamilton, so this will have 12 factorial different Hamiltonian circuits. So there's an abundance of Hamiltonian circuits, and they just keep going. I don't know why I did that. I guess I got excited. So some applications we talked about a little bit, but one application I will share with you, and then I guess we're going to have to leave, is this one. If you were to help me plan my spring break trip, what we love about spring break, my wife and I, is going and visiting family. And so I have here Columbus Airport in the middle, and then the Palm Springs Airport over there on the left where my sister lives, the Raleigh-Durham Airport down at the bottom where my one daughter lives, and then the Boston Airport where I have 2 daughters. And so these prices, though, are a couple of years old. I don't know what the prices would be nowadays for flights. But anyway, you can imagine the situation is that I'm interested in finding a Hamiltonian circuit. I'd like to start in Columbus, go visit those 3 other places, and then go back to Columbus. That's a Hamiltonian circuit. And I'd like to do it in the cheapest possible way. And so not only do we want a Hamiltonian circuit, but we want to come up with a Hamiltonian circuit that is the cheapest possible Hamiltonian circuit. So you can certainly do this for me. It's not difficult to find the cheapest possible Hamiltonian circuit here. However, if you're doing that with, there's another grid that, where did it go? I don't see it. Oh, there it is, this. So you might wonder, what is this? Well, this is sort of a similar situation to my spring break trip that I'd like to take, except that now I have, what is that, 5, 10 cities that I'm visiting. And those numbers there represent the cost to go between those 2 cities. So for example, flying from city A to city D costs $152. So here again, I want to find the cheapest possible Hamiltonian circuit visiting all 10 of those cities and going back home. But it's much more complicated. In fact, over here, there's, with this, there are only 3 possible Hamiltonian circuits that you could come up with. Whereas with this 10 thing, there's way more. So it's like 500,000 with that one. So anyway, we'll do that, I guess, on Wednesday, and I'm going to just shift everything. So if you get ahead of me and you take a look at the homework before I get to editing it, just do the ones that talk about Eulerizing and the basic Hamiltonian, nothing that looks like this. In fact, I'll go in there. I'll fix it eventually. Yeah.
Do you want the homework that was due before our test?
No, don't do it. Because that's going to confuse everyone. We had homework? Yeah, before the test.
Yeah.
There's like,
Yeah.
yeah, I'm sure everyone did it. I'll just give everyone credit for it. And then, that way I don't have to do, because I still have a stack of papers in my office. I always prioritize tests. Tests, they all go back day after. Speaking of day after, there is, I think, do you have the surveys, end of course surveys? Or is that this coming weekend?
Is it?
I don't know. When you do it, yeah, remember my tests, I always hand back the test day after. It doesn't matter. Quizzes, not as important as tests. Tests are super important. So, yeah, I'll remind, maybe end of the week, I'll remind you to do the end of course surveys. And I'll even give you the answers if you don't know what they are. So. All right, what do you got, Peyton? Do I owe you a point?
I was just wondering why I missed 5.
Okay, so this is let's see, inclusion, exclusion. So wait, I have no idea. That is so bizarre. Because
and each question's worth 4.
it is worth 4. That's ridiculous. I think it's.
And I kind of got half of it.
You got half of it. I think I was thinking it was out of 10. My calculator, each problem was worth 10, and I was talking toggling back and forth. I must have just not thought. So did I do this to you more than once? Oh, no, that one, I did that one correctly, because that's like, yeah, that should be minus. I mean, the minuses don't even add up. What in the world? Oh, no, there's a 3 there.
Yeah, it's minus 3. What?
But that should be,
one too.
yeah, that should be, because you got this one right. I was thinking these were separate, but they aren't lettered, so each of these is each 4. Yeah, I blew it. I ripped you off. I hope I didn't rip anyone else off. I'll need to take this. But yeah, that should only be minus 2. Yeah, you
Do you
definitely
want
do.
it, or?
Yeah, I want to keep it because I can fix this. That should be either minus 1. It's probably minus 1. That should be a minus 1, minus 2, which makes it at 93. I'll add it up. I'll do it right. I'll do it right. I apologize.
That's alright, thank you.
Totally ripped you off. That'll help me to remember to bring stickers next time because you deserve a sticker. Evan. Cooper. Are you on Team Jesus? You're doing security for Team Jesus. Wait, that's not you. Sorry, I said Evan. I gave it to Cooper. I'll give you a minute here, Cooper. Yours is towards the bottom. This person. Sarah. David. Woo! Okay. Yeah, I don't need help planning my spring break trip. We'll discard that. Find what we're doing in here. Let's make it big.